Look up at the night sky and you'll see pinpricks of light stars, galaxies, the grand tapestry of the cosmos as we know it. But what if I told you there's something hidden out there, something so strange and powerful, it might hold the secret to existence itself? I'm talking about black holes, cosmic monsters so dense that not even light can escape their pull. For decades, they've captured our imagination and challenged our understanding of reality. But what if these mysterious giants aren't just in points? What if instead of being tombs for matter and energy, they're actually cradles for entirely new universes? It sounds like science fiction, but some of the brightest minds in physics are asking this very question. Could a black hole be the birthplace of another cosmos? Imagine our universe not as a one-off miracle, but as one branch in an infinite cosmic family tree, a tree where each black hole might sprout a new reality, with its own laws of physics, its own stars, its own possibilities. This idea stretches the limits of our imagination, blurring the line between destruction and creation, ending and beginning. It suggests that every time a star collapses into a black hole, it might not be vanishing into nothingness, it might be giving birth. Today, we're going to explore this breathtaking possibility. We'll dive into the cutting-edge theories that suggest black holes could be portals to other universes, examine what happens at the very edge of a singularity, and ask what it would mean if our universe itself was born from a black hole in another cosmos. This isn't just about mind-bending physics, it's about our place in something vastly larger and more mysterious than we ever dreamed. So come with me on this journey as we venture into the heart of darkness to ask one of the most profound questions ever posed. Are black holes the mothers of new realities? To grasp how something as destructive as a black hole could possibly create, we first need to understand what it truly is. Picture a star far more massive than our own sun. For millions of years, it burns brightly, an epic battle between the outward push of nuclear fusion and the inward crush of its own immense gravity. Eventually, that star exhausts its nuclear fuel. The battle ends and gravity wins. In a cataclysmic instant, the star's core collapses. If it's massive enough, nothing in the known universe can stop it from squeezing all that matter into an infinitesimally small point. This is the birth of a black hole. What defines a black hole isn't just its mass, but its incredible density. It possesses such a powerful gravitational pull that within a certain distance from its center, the escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing can escape. This boundary is called the event horizon. It's not a physical surface you could touch, it's a point of no return. Think of it like a cosmic waterfall. If you're in a boat far upstream, you can easily paddle to safety. But once you cross the edge of the waterfall, the current becomes irresistible. The event horizon is that edge. Inside that boundary, all known laws of physics break down. The matter that once was a star continues to collapse, crushed by gravity to a point of zero volume and infinite density. This is the singularity, the true, terrifying heart of the black hole. It's a place where the rules of space and time as we know them cease to exist, and they come in astonishing varieties. Stellar mass black holes, the ones formed from dying stars, can be 10 or 20 times the mass of our Sun. Then there are the supermassive black holes lurking at the centers of galaxies like our own Milky Way. These behemoths are millions, even billions of times more massive than the Sun, and we're still unraveling the mystery of how they grew so large. There are even intermediate mass black holes, the elusive missing link between the two. Each type is a gravitational monster, but they all share that same fundamental anatomy, an event horizon cloaking a singularity. It's this bizarre and extreme environment that leads some physicists to propose a truly radical idea that a black hole's singularity might not be an end but a new beginning. So we arrive at the singularity, the final destination of our cosmic waterfall analogy. This is the point where our understanding doesn't just get strained, it shatters completely. Our two most successful theories of reality, the twin pillars of modern physics, give us completely contradictory and frankly nonsensical answers about what happens here. On one hand, we have Einstein's general relativity, which describes gravity as the curvature of spacetime. It tells us that the matter falling into the black hole gets crushed into an infinitely tiny point of infinite density. But in physics, infinity is almost always a sign that your theory is incomplete. It's a mathematical placeholder for we don't know what happens here. An infinitely dense point isn't a physical object, it's a paradox. And here's where our other great theory, quantum mechanics, should step in. Quantum mechanics perfectly describes the behavior of the very small atoms and subatomic particles. It tells us there's a fundamental graininess to the universe, a smallest possible scale. You cannot have an infinitely small point, there is a limit. But when we try to apply the rules of quantum mechanics to the intense gravitational field of a singularity, the math fails spectacularly, the equations blow up. It's like trying to use a recipe for a cake to build a skyscraper. The instructions just don't apply at that scale. This clash is known as the problem of quantum gravity, and the singularity is its ground zero. Think of it like this. General relativity paints a beautiful, continuous picture of spacetime as a smooth fabric. Quantum mechanics reveals that this fabric is actually woven from tiny, discrete, jittering threads. At the singularity, the smooth fabric is wound so tightly that it should tear, and we need a theory that can describe those individual threads under unimaginable strain. We simply don't have that theory yet. This isn't a minor gap in our knowledge, it's a yawning chasm right at the heart of our understanding of the cosmos. This profound failure is precisely why some physicists suspect that the singularity isn't a real physical endpoint. They propose that our equations are merely pointing us toward a deeper truth, that the extreme conditions at the center of a black hole act as a sort of cosmic pressure valve. Just as water heating in a kettle turns to steam and expands, the unimaginable compression might trigger a transformative process, a quantum rebound or a tunneling into an entirely new state of existence. The infinite density might be a signal not of an end, but of a transition into a new set of physical laws, perhaps even birthing a new spacetime altogether. The very point where our physics breaks down could be the very point where a new universe begins. This clash between our two great theories, the smooth fabric of relativity and the jittery grains of quantum mechanics, is what drives the search for a deeper truth. And one of the most profound attempts to resolve this conflict comes from a true giant of theoretical physics, Sir Roger Penrose. A Nobel laureate and one of the minds who helped prove the mathematics behind black hole formation, Penrose looked into the abyss of the singularity and saw not just an end but a potential doorway. His theory is called conformal cyclic cosmology, or CCC, and it proposes a vision of existence that is both humbling and magnificent. It suggests that our universe is not the first and only universe, but merely one episode in an endless, perhaps beginningless cycle. In this view, the cosmos has no definitive start and no final death. Instead, it goes through immense epochs which Penrose calls eons. Each eon begins with a hot, dense Big Bang and expands over trillions of years into a cold, empty, lifeless void. But that emptiness, that end, becomes the seed for the next beginning. The key to this incredible idea is a mathematical transformation. Penrose realized that as a universe expands and cools toward its final state, all the matter and energy eventually dissipate. Particles decay, black holes evaporate through Hawking radiation, and all that's left is a vast sea of low-energy photons, light spread infinitely thin. In this state, the concept of distance and time loses all meaning. There are no objects to measure, no events to mark the passage of time. The geometry of this empty, timeless end state becomes mathematically identical to the hot, dense, small, and timeless beginning of a new Big Bang. The infinite future of one eon smoothly connects to the singularity of the next. The end becomes the beginning. So where do black holes fit into this grand cycle? They are the cosmic messengers, the carriers of information from one eon to the next. Penrose suggests that the evaporation of every single black hole leaves behind an indelible imprint on the fabric of spacetime. This imprint, a form of gravitational wave or energy signature, doesn't vanish when the universe ends. Instead, it gets transferred through that mathematical bridge into the next eon. These imprints might even be detectable in our universe today as faint, circular patterns in the cosmic microwave background radiation, the faint afterglow of our own Big Bang. If confirmed, these Hawking points would be the ultimate evidence, a fossilized message from a universe that existed before our own, delivered by black holes that died eons ago. It's a breathtakingly elegant and optimistic vision. Instead of a lonely universe facing a cold, empty heat death, we are part of an infinite, recycling cosmos. Every ending contains the spark of a new beginning, and the most destructive objects in existence become the scribes that preserve information across eternity. Penrose's theory challenges us to see the entire timeline of existence, from the first flash of light to the last fading ember, as one continuous, unbreakable loop. While Penrose's vision is one of elegant mathematical cycles, another physicist, Lee Smolin, offers a theory that is equally grand but framed in strikingly biological terms. He asks a radical question: what if the laws of physics aren't fixed and eternal, but are instead subject to change, mutation, and evolution? This idea forms the core of his theory of cosmological natural selection, a hypothesis that applies the principles of Darwinian evolution to the cosmos itself. In this breathtaking view, our universe isn't a static arena. It's a participant in a vast cosmic ecosystem, and its most successful trait is its ability to create black holes. Think about how natural selection works in biology. Organisms that are better adapted to their environment are more likely to survive, reproduce, and pass on their genes. Over countless generations, this process leads to the incredible diversity and fine-tuning we see in life on Earth. Smolin proposes a stunning cosmic parallel. He suggests that every time a black hole forms, the extreme conditions at its core don't just collapse into a singularity, they trigger the birth of an entirely new universe. This new universe inflates, expands, and develops its own laws of physics. But crucially, those laws aren't an exact copy of the parent universes. They are slightly mutated, tweaked, and changed. This is the mechanism for cosmic evolution. Each new universe is a kind of offspring, inheriting most of its parent's physical traits like the strength of gravity, the mass of an electron, or the cosmological constant, but with small, random variations. Some of these new universes might have constants that make them stillborn. Perhaps gravity is so strong that everything instantly collapses, or so weak that stars and galaxies can never form. Other universes, like our own, have constants that allow for the long, stable processes needed to form stars, planets, and ultimately black holes, and that is the key to the whole process. The universes that are most fit in this cosmic landscape are the ones that can produce the most black holes. Why? Because each black hole is a potential portal for creating a new universe, a new branch on the cosmic family tree. A universe that is efficient at making black holes will have a lot of offspring, and those offspring will inherit its successful black hole, producing physical constants. Over countless generations of universes, the laws of physics themselves evolved toward those parameters that maximize the production of black holes. It's a powerful, elegant feedback loop. Success is measured in gravitational collapse. This theory also offers a potential answer to one of the most perplexing questions in all of science. Why does our universe seem so perfectly fine-tuned for life? The fundamental constants of nature appear to be set with incredible precision. If the force of gravity were even slightly stronger or weaker, if the proton were a tiny bit heavier, if the cosmological constant weren't so exquisitely balanced, stars wouldn't burn, atoms wouldn't form, and life as we know it would be impossible. To many, this seems like an unbelievable coincidence. Some invoke a divine creator or the anthropic principle, the idea that we can only observe a universe that allows for our existence. But Smolin's theory provides a purely natural, physical explanation. Our universe isn't fine-tuned for us, it's fine-tuned for making black holes. It just so happens that the very same conditions that allow for a prolific number of black holes, stable, long-lived stars, the right nuclear forces for supernova, galaxies that can collide and merge, are also the conditions that allow for the emergence of complex structures like planets and life. We are not the target of this cosmic evolution, we are a fortunate byproduct. The universe makes black holes, and we are along for the ride, of course. Like any bold theory, cosmological natural selection faces its share of challenges and criticisms. The most significant is its current lack of direct testability. How do we observe other universes to see if their physical constants are indeed mutated? Smolin himself has proposed some potential tests, such as predicting the most probable values for certain constants based on black hole production, which could then be checked against our own universe's values. But for now, it remains a deeply compelling and imaginative framework, a story that connects the vast to the microscopic, the beginning to the end, in a grand narrative of cosmic birth and evolution. It suggests that the black holes we observe are not just in points, but are, in a very real sense, cosmic seeds. But to find a way out of this theoretical dead end, we must look beyond our current physics and toward the ambitious quest for a theory of everything, a single framework that can seamlessly unite the cosmic scale of gravity with the quantum world. One of the leading contenders in this quest is called loop quantum gravity, and it offers a radically different and far less destructive vision of what happens at the heart of a black hole. This theory suggests that the fabric of spacetime isn't smooth and continuous, but is instead woven from tiny, indivisible loops, a kind of one-dimensional fabric of reality. And this granular structure has a profound implication. It prevents matter from being crushed into an infinitely dense point. Instead of a catastrophic singularity, loop quantum gravity predicts a cosmic reprieve. The incredible gravitational squeeze reaches a point where it can compress no further, and the granular nature of spacetime itself acts like an ultimate spring, pushing back. This leads to a monumental rebound, a bounce. The collapsing matter hits this barrier and then explosively reverses its course. Now, imagine that reversal happening not back into our own universe, but into an entirely new region of spacetime. The black hole, in this view, becomes a tunnel, a bridge from our cosmos to another. This is where we encounter one of the most mind-bending concepts in all of theoretical physics, the white hole. If a black hole is a region of spacetime from which nothing can escape, a white hole is its theoretical opposite, a region of spacetime into which nothing can enter. It would be a source of matter and energy that only pours outward, a cosmic geyser erupting into existence. For a long time, white holes were considered little more than mathematical curiosities, improbable solutions to Einstein's equations that were unlikely to exist in the real world. But within the framework of loop quantum gravity, they become a compelling possibility. The bounce at the center of a black hole could be the moment it transforms into a white hole, spewing all that ingested material out into a new reality. Think of it not as an explosion in our space, but as the birth of a new spacetime altogether. The white hole's eruption would be that new universe's Big Bang. The entire history of that new cosmos, its expansion, the formation of its galaxies and laws of physics would all be the aftermath of a black hole collapse in a parent universe. This provides a stunningly elegant mechanism for the creation of new universes, one that sidesteps the dreaded singularity entirely. The matter isn't destroyed, it's repurposed. The energy isn't lost, it's recycled. A death in one world gives life to another. This idea naturally leads to the concept of a wormhole, a speculative tunnel connecting these 2 points in space-time. In this scenario, the black hole in our universe and the white hole in the new one could be 2 ends of the same bridge, a direct umbilical cord between parent and offspring. Of course, this tunnel would be incredibly unstable and would likely pinch off almost instantly, severing the connection and ensuring the 2 universes evolve independently, forever separated by the vast gulf of their own expanding realities. We could never travel through it or observe the new universe directly, which makes the idea incredibly difficult to test. But as a theoretical proposition, it offers a beautiful and physically plausible narrative for cosmic creation, turning the most ominous objects in the sky into potential cosmic nurseries. So if the singularity isn't a true end, what actually replaces it? This is where quantum gravity offers its most radical revision. The leading idea is that the collapse doesn't continue to an infinitely small point. Instead, the quantum properties of spacetime itself put a hard limit on the compression. Imagine pushing down on a spring. At first, it compresses easily, but the closer it gets to its absolute limit, the more it pushes back. Now picture that spring not as a physical object, but as the very fabric of reality. At a certain unimaginable density, the quantum structure of spacetime provides the ultimate resistance. The crushing collapse stops and reverses in a tremendous rebound, a quantum bounce. This bounce isn't like a ball hitting the ground and coming back up into the same space. The physics suggests this reversal could channel all that energy and matter into an entirely new region of spacetime, initiating a rapid, explosive expansion. This is the moment of creation. The white hole eruption we discussed becomes the big bang for a new cosmos, forever separate from our own. The black hole in our universe becomes a one-way door. What goes in doesn't come out to us, but serves as the raw material for an entirely new reality. To visualize this, think of the geometry not as a bottomless pit, but as a tunnel or a bridge. The extreme gravity of the black hole warps spacetime so severely that it effectively stitches itself to a new, nascent universe. This bridge, however, is almost certainly transient. It would likely exist for only a fleeting instant before pinching off, severing the connection completely and leaving the 2 universes to evolve independently. This process transforms the black hole from a destructive grave into a creative nexus, a cosmic recycler on the grandest possible scale. This brings us to one of the most famous and frustrating puzzles in all of modern physics, a problem that Stephen Hawking himself identified, and that connects the fate of information directly to the fate of universes, the black hole information paradox. To understand why this is such a big deal, we need to consider one of the most fundamental principles in quantum mechanics, the law of information conservation. This law states that information, the specific, unique quantum state of every particle, like its spin, momentum, and energy, can never be truly destroyed. It might be scrambled, transformed, or hidden, but it must in principle be recoverable. Think of it like burning a book. The book appears gone, reduced to ash and smoke. But if you could somehow collect every single atom of ash and every molecule of smoke and track their precise paths and interactions, you could theoretically reconstruct the exact text on every page. The information still exists in the universe, it's just incredibly difficult to reassemble. For a long time, physicists assumed this principle held true even for black holes. Then, in the 1970s, Stephen Hawking made a stunning discovery. He realized that due to quantum effects at the very edge of the event horizon, black holes aren't completely black. They slowly leak energy. This phenomenon, now called Hawking radiation, causes a black hole to gradually lose mass and, over astronomical timescales, completely evaporate, vanishing from existence. Here's the catch. Hawking's calculations showed that this radiation is purely thermal. It's random, featureless heat like the glow from a stove element. It contains no information whatsoever about the specific matter that fell in. A black hole that consumes a book, a star, or a million elephants would all produce the exact same generic Hawking radiation. When the black hole finally evaporates, all that unique quantum information seems to have been erased from reality, violating a core tenet of quantum physics. This is the information paradox. It suggests that our understanding of either quantum mechanics or general relativity is fundamentally, catastrophically wrong. For decades, this paradox haunted theoretical physics. It set up a seemingly irreconcilable conflict, a choose-your-own-adventure of scientific despair. Either information is lost, which forces a rewrite of quantum mechanics, or general relativity's depiction of the event horizon as a point of no return is incorrect. Most physicists strongly believe information must be preserved. The question has always been how and where. This is where the idea of black holes as universe creators offers a breathtakingly elegant and profound solution. If a black hole doesn't simply trap information behind an event horizon until it evaporates into nothing, but instead funnels that information into the birth of a new spacetime, then the paradox might simply vanish. Imagine our parent universe's black hole not as a cosmic trash compactor, but as a cosmic scanner. It takes all the information of everything that falls in every atom, every particle, every bit of data that defines what something is, and it doesn't destroy it. Instead, it imprints that information onto the very fabric of the new universe it spawns. The specific quantum states of the matter that collapsed could directly influence the initial conditions of the new Big Bang, perhaps setting its fundamental constants or seeding the density variations that would later form galaxies. In this scenario, the information isn't lost at all, it's transferred. It becomes part of the genetic code of a new cosmic offspring. The Hawking radiation we see in our universe is just the leftover, thermal exhaust from this incredible process of cosmic reproduction. The valuable data has been safely shipped to a new reality. This provides a stunningly clean resolution to the paradox. Information is conserved, but not in our universe. It's preserved in the structure of a child universe. We can't access it, which is why, from our limited perspective inside the parent universe, it appears to be gone. But from a grand, multiversal perspective, no information is ever destroyed. This idea turns the act of falling into a black hole from the ultimate annihilation into the ultimate act of cosmic legacy. Every particle that crosses the event horizon contributes its unique quantum signature to the genesis of a new cosmos. The information paradox, a problem that has defined theoretical physics for half a century, might not be a paradox at all. It might simply be a sign that we've been thinking too small, and that the true story of existence is written not in a single universe, but in a vast, branching tree of life, death, and rebirth on the grandest scale imaginable. The beauty of these mind-bending ideas isn't just in their grand narrative, it's in the rigorous mathematics that gives them weight. While we can't dive into postgraduate level equations here, we can appreciate the fundamental shapes and forms this math takes, the elegant diagrams and concepts that allow physicists to even propose such astounding possibilities. It all begins with a simple yet profound shift in how we draw the universe. Sir Roger Penrose gave us a powerful new way to map reality using what are called conformal diagrams, also known as Penrose diagrams. Think of a standard map of the world. The globe is a sphere, but to put it on a flat page, we use a projection that inevitably distorts sizes or distances. Think of how Greenland looks enormous on a Mercator map next to Africa. A conformal diagram is a special kind of projection for spacetime. It cleverly squishes the infinite distances of the universe and the infinite future of time into a finite, diamond-shaped drawing. The key is that while it distances and times, it perfectly preserves the angles at which light rays travel. Since light defines the fundamental causal structure of the universe, what can influence what this diagram shows us the true story of cause and effect? On this diagram, the edge of the diamond isn't a physical barrier, it represents infinity. The journey of a light ray is always drawn at a perfect 45-degree angle. The event horizon of a black hole becomes a line also at 45 degrees, leading to the singularity, which is now represented not as a point but as a jagged, horizontal line, a true boundary where time itself ends. This is where Penrose's genius for conformal cyclic cosmology shines. He saw that the mathematical description of this empty, timeless infinity at the end of one universe is identical to the hot, dense, timeless singularity at the beginning of another. The equations match. The conformal diagram of one eon seamlessly connects to the next, creating a continuous, unbroken chain. The math shows that nothing and everything can be two sides of the same coin. Now, let's turn to the equations that rescue us from the singularity. In loop quantum gravity, the key idea is that space itself is not smooth and continuous, but is made of tiny, indivisible units. Think of it as a fabric woven from one-dimensional loops. This is described by a complex mathematical object called a spin network. The equations governing these networks prevent the infinite curvature of a singularity. Instead of density soaring to infinity, the quantum geometry provides a tremendous repulsive force. The central equation governing the collapse effectively flips a sign from negative to positive, turning the irresistible gravitational crush into a powerful quantum bounce. We can represent this with a modified version of the famous Friedmann equations, which describe the expansion of the universe. In standard cosmology, these equations show the scale factor of the universe, essentially its size, approaching zero at the Big Bang singularity. But in loop quantum cosmology, a term appears in the equation that represents this quantum repulsion. It looks something like this. The energy density ρ is not allowed to exceed a critical density ρ crit. This creates a barrier. As the collapsing matter in a black hole approaches ρ crit, the equation for the rate of collapse includes a term like 1 ρ/ρ crit, which suddenly goes to zero and then becomes negative, reversing the collapse into an expansion. This is the mathematical heart of the bounce, the moment a black hole's death becomes a white hole's birth. Finally, we have the mathematical language of wormholes described by solutions to Einstein's field equations. The most famous is the Einstein-Rosen bridge, which mathematically connects a black hole to a white hole. The equations describe a tunnel or throat that is initially open but is predicted to pinch off instantly due to its unstable nature. The Kretschmann scalar, a quantity calculated from the curvature of spacetime, remains finite throughout this process in loop quantum gravity models, unlike in classical physics where it blows up to infinity at the singularity. This finitude is the mathematical proof that the journey through the bridge is not doomed. There is no infinite tidal force to destroy everything. The numbers tell a story of a passage that, while likely transient, is physically possible, transforming a point of infinite destruction into a gateway of creation. So where does this incredible idea of black holes as cosmic parents fit into our modern scientific view of reality? It turns out it's not the only game in town. The concept of a multiverse, a vast collection of universes beyond our own, has moved from the fringe of philosophy to a serious subject of scientific discussion, and it appears in several strikingly different forms. Understanding these variations helps us see just how radical and unique the black hole genesis theory truly is. Perhaps the most prominent multiverse concept comes from the theory of cosmic inflation, the idea that our universe underwent a period of exponential expansion just after the Big Bang. This theory elegantly solves several major cosmological puzzles, but it also suggests something profound. Once inflation starts, it may be eternal. The driving force behind it, a strange high-energy field called the inflaton, might cause space to expand so rapidly that it continually creates new pocket universes in a vast, ever-growing foam. In this inflationary multiverse, each of these bubbles is a separate universe, each with its own Big Bang, and potentially its own random set of physical constants and laws. It's a cosmic lottery on an infinite scale, and we just happen to live in a bubble where the numbers came up right for life. It's a powerful idea, but it's also a bit impersonal. The creation of new universes is a blind, mechanical process driven by the relentless decay of an energy field. Then there's the multiverse predicted by the many worlds interpretation of quantum mechanics. This one is born from the strange behavior of the very small. In the quantum realm, particles exist in a haze of probability, and every possible outcome of a quantum event is realized. This interpretation suggests that the entire universe splits into multiple branches every time a quantum decision is made. Did that electron go left or right? The universe divides, creating one timeline where it went left and another where it went right. This results in a mind-bogglingly vast tree of parallel realities, encompassing every possible variation of history. But these are all variations of our universe. They all share the same fundamental physical laws and constants, just different historical events. It's a multiverse of possibilities, not a multiverse of different physics. String theory, our most ambitious attempt to unify all forces of nature, offers yet another vision, the landscape multiverse. This theory proposes that the fundamental building blocks of reality are tiny, vibrating strings. The way these strings vibrate determines the properties of particles and forces. But the mathematics of string theory suggests there isn't just one unique way for these strings to settle into a stable configuration. There might be a colossal number of possible stable states, perhaps 10 to the 500 or more. Each of these states corresponds to a universe with a completely different set of physical laws. In this landscape, our universe is just one valley among countless others, each with its own unique terrain of physics. Finding ourselves in a life-friendly universe is like finding a single specific grain of sand on a planet-sized beach. Now place the black hole theory onto this map. It's fundamentally different. Unlike the inflationary multiverse, where new universes are born from the decay of a field, or the string theory landscape, where they exist as static possibilities, the black hole genesis theory is dynastic and evolutionary. It proposes a physical mechanism, gravitational collapse, that actively creates new universes. It's not a random lottery or a static landscape. It's a cosmic family tree. Each new universe is an offspring, inheriting traits from its parent but with slight mutations. This introduces a direction and a purpose to the multiverse that the other theories lack, the drive to produce more black holes. It's a multiverse shaped by evolution and selection, not just chance. This theory also provides a potential answer to the fine-tuning problem that the other multiverses merely accept. In the inflationary or string theory landscapes, we just got lucky. In the black hole multiverse, our universe's laws aren't random. They are the product of generations of selection for universes that are stable, long-lived, and proficient at making black holes. The constants are the way they are because those are the constants that lead to prolific reproduction. Life is a fortunate byproduct of that cosmic fertility. Each of these multiverse theories offers a different lens on reality. Inflation gives us a bubbling cosmic foam. Many worlds gives us branching timelines. String theory gives us a vast, frozen landscape of possibilities. But the black hole genesis theory gives us something uniquely biological, a living, breathing, evolving cosmos where death gives birth to new life on the grandest scale, and every singularity is a story waiting to be told. But how do we move from these beautiful mathematical speculations to something we can actually observe? How do we test an idea as grand as a universe being born from a black hole? We look for a message from the beginning of time itself, etched into the oldest light in the cosmos. This is the cosmic microwave background radiation, or CMB. It's the faint, cold glow that fills every corner of space, the cooled-down remnant of the universe's fiery birth in the Big Bang. For cosmologists, it's a fossilized snapshot of the infant universe, and within its subtle patterns, we might just find evidence of events that occurred before our universe even began. This brings us back to Roger Penrose and his conformal cyclic cosmology. If our universe was indeed born from the death of a previous one, that event should have left a mark. Specifically, Penrose calculated that the colossal gravitational waves generated by the collision of supermassive black holes in the previous eon would not be entirely lost when that universe met its end. As that universe expanded into nothingness and transformed into the hot, dense state of our Big Bang, those waves would be imprinted onto the new cosmos as faint, circular patterns of temperature variation in the CMB. These patterns, which he calls Hawking points in honor of Stephen Hawking, would be like ghostly fingerprints left on the windowpane of our cosmos by the giants of a world long gone. In 2010, Penrose and his colleague Vark made a stunning announcement. After analyzing data from NASA WMAP satellite, which had mapped the CMB in exquisite detail, they claimed to have found exactly that, a series of concentric rings within the microwave background where the temperature variations were inexplicably low. They argued these rings were precisely the kind of signatures predicted by his theory, potential evidence of a pre-Big Bang universe. The scientific community, naturally, was electrified and deeply skeptical. Extraordinary claims require extraordinary evidence, and the hunt was on. Other teams of researchers rushed to analyze the same data, as well as newer, even more precise data from the European Space Agency's Planck satellite. The results of these investigations have been mixed and have sparked a vigorous, ongoing debate. Some analyses seem to confirm the presence of these unusual concentric circles, while others attributed them to known effects, like the way data is processed and mapped onto a sphere, or even to random statistical fluctuations in the cosmic noise. The central criticism is that the universe is a very lumpy place, and finding patterns in random noise is a known pitfall in statistics, a phenomenon called apophenia, where we see meaningful shapes in random data, like finding animals in the clouds. The debate over these circles is a perfect example of the scientific process at its most rigorous and frustrating. It's a high-stakes game where every claim is met with intense scrutiny. Proponents argue that the specific nature and distribution of these circles are unlikely to occur by chance. Detractors counter that until we can completely rule out all other possible explanations, including unknown instrumental effects or more mundane astrophysical processes, the rings remain an intriguing curiosity rather than proven evidence. This back and forth isn't a weakness of science, it's its greatest strength. It forces ideas to prove their worth against every conceivable challenge. The search for a primordial signal doesn't end with circles. Other potential signatures are being investigated. Could there be a specific statistical anomaly in the way temperatures vary across the sky? Might there be a preferred direction or axis, a kind of cosmic handedness inherited from the parent universe? Perhaps the key lies in the polarization of the CMB light, the specific direction its waves vibrate, which could carry a cleaner record of these unimaginably ancient events. Each new generation of telescopes and satellites, each more sensitive than the last, gives us a sharper image of this cosmic fossil, offering a better chance to find these subtle ghosts in the machine. Whether Penrose's circles are ultimately confirmed or dismissed, the very act of looking is what matters. It transforms a philosophical question about our origins into an empirical, testable scientific one. We are no longer just asking what if, we are actively scouring the sky for answers. The cosmic microwave background is our most direct link to the ultimate beginning. And if that beginning was itself an ending, the evidence must be hiding in that ancient light, waiting for us to develop the tools and the wisdom to read its story. While the cosmic microwave background offers a fossilized glimpse into the very early universe, a brand new window onto the cosmos has been flung open, one that could let us listen in on the most violent events in existence and perhaps even hear the whispers of creation itself. This is the era of gravitational wave astronomy. In 2015, the LIGO Observatory made history by directly detecting these ripples in the fabric of spacetime, caused by the colossal collision of two black holes over 1 billion light-years away. This wasn't just confirming Einstein's prediction, it was handing us an entirely new sense with which to perceive the universe. We are no longer just stargazers, we have become universe listeners. Gravitational waves are the ultimate messengers from the edge of reality. Unlike light, which can be absorbed, reflected, or obscured by dust, these ripples travel almost completely unimpeded across the cosmos, carrying with them a pure, undistorted record of the cataclysm that created them. When two black holes spiral inward and merge, they don't just create a simple splash. They generate a complex chord, a rising chirp that encodes incredibly precise information about their masses, their spins, and the very nature of the spacetime they're warping. By carefully studying the intricate details of this signal, physicists can perform a kind of cosmic autopsy, reverse engineering the event to understand what happened in those final frenzied moments. This is where the theories of universe creation come into play. According to the standard model of black holes, the merger should produce a clean, predictable signal that settles down into the calm hum of a new, larger black hole, what is known as the ring down. But what if the exotic physics at play, the quantum bounce, the transformation into a white hole, the tunnel to another universe, left a subtle fingerprint on that signal? If the interior of a black hole isn't a classical singularity but something else entirely, the gravitational waves emanating from a merger might carry a faint, telltale echo of that bizarre physics. Imagine the final plunge of two black holes. In the standard view, their two singularities merge into one. But in the quantum bounce or white hole scenario, the incredible energy of the collision might not just form a new event horizon. It could trigger a rebound effect or momentarily stabilize a bridge to another spacetime. This wouldn't just stop the gravitational waves, it would add a new, complex layer to them. The main chirp of the merger might be followed by a series of faint, repeating after vibrations echoes. These wouldn't be echoes in space like sound bouncing off a wall, but echoes in the signal itself, caused by the gravitational waves briefly becoming trapped in the quantum foam-like structure just outside the final event horizon before leaking out. A few years ago, a team of physicists analyzed the early LIGO data and reported they might have found precisely these kinds of statistical hints of echoes following several black hole mergers. The scientific community, much like with the CMB circles, responded with intense interest and healthy skepticism. Could this be instrumental noise, a glitch in the incredibly sensitive detectors, or something more profound? The search for these echoes has become a fierce frontier of research. As our detectors like LIGO, Virgo, and the future space-based observatory LISA become more and more sensitive, they will be able to gather cleaner data and either confirm these tentative findings or rule them out entirely. Beyond echoes, there are other potential signatures. The precise frequency and decay rate of the ring-down signal are exquisitely sensitive to the nature of the object left behind. A classic black hole with its perfect event horizon has a specific ring-down signature. An exotic object like a hypothetical gravistar with a dark energy core or a quantum bounce region would ring down differently. It would be like listening to a bell. Your ear can tell the difference between a bell made of brass and one made of glass just by the sound it makes when struck. Similarly, the sound of the merging black holes could tell us if we're hearing a standard event horizon or something far stranger that doesn't completely obey Einstein's classical rules. Finding such a signature wouldn't just be a minor adjustment to our theories, it would be a revolution. It would be direct observational evidence that our understanding of the black hole interior is wrong, and that something truly exotic is happening at the point where we expect a singularity. It wouldn't immediately prove the universe birth hypothesis, but it would open the door wide open. It would show that the laws of physics do indeed provide an escape from the infinite curvature of a singularity, which is the essential first step for any theory that turns a black hole into a birthplace. With every new black hole merger we detect, we are collecting more data, more chords in the symphony of space-time, each one a potential carrier of the deepest secret of the cosmos. We are learning to listen not just for the death of stars, but for the possible birth cries of new worlds. This brings us to a concept that seems to come straight from the pages of a science fantasy novel, but is in fact a cornerstone of modern theoretical physics: the idea that black holes have temperature and, even more bizarrely, entropy. To see why this is so revolutionary, we need to understand what entropy represents. In our everyday world, entropy is a measure of disorder, of the number of ways you can rearrange the pieces of a system without changing its overall appearance. A tidy room has low entropy, a messy room has high entropy. A pure crystal has low entropy, that same crystal smashed into a pile of dust has high entropy. It's a measure of hidden information, the number of microscopic arrangements that could produce the same macroscopic state. Now, consider a classical black hole from Einstein's general relativity. It's defined by just three properties: its mass, its electric charge, and its spin. It doesn't matter what you throw into it: a library of every book ever written, a complex supercomputer, or a cloud of pure hydrogen gas. Once it crosses the event horizon, the black hole just gets a little more massive. Its spin might change slightly, but that's it. All the intricate, unique information about what it consumed is seemingly erased, scrubbed clean. It's the ultimate simplifier. According to the classical rules, a black hole should have zero entropy. It is the most ordered, least disordered object conceivable. But this created a huge problem because it seemed to violate the second law of thermodynamics, which states that the total entropy of the universe must always increase. The genius of Jacob Bekenstein and Stephen Hawking was to realize that this classical picture was profoundly wrong. Bekenstein, a young graduate student, made a bold proposal. He argued that a black hole must actually have entropy, and an enormous amount of it. In fact, he showed that the entropy of a black hole is proportional to the surface area of its event horizon. This was a staggering idea. In every other system we know, entropy is proportional to volume. A bigger box can hold more disorder than a smaller one. But for a black hole, the entropy is tied to its surface area. It's as if all the information about everything that ever fell into it is not stored in its volume, but is somehow encoded on its two-dimensional boundary, its outer shell. This is the famous holographic principle in its earliest form. Then Hawking took this idea and ran with it, applying quantum mechanics to the curved spacetime around a black hole. His stunning discovery was that black holes aren't completely black, they radiate, they have a temperature, and if something has a temperature, it unequivocally has entropy. Hawking's calculations confirmed Bekenstein's audacious idea and even provided the exact formula. The entropy of a black hole is literally astronomical. A single stellar mass black hole can have an entropy value that is orders of magnitude greater than the combined entropy of every star, planet, and particle in the entire visible universe. It is, by an almost incomprehensible margin, the greatest reservoir of entropy and information in our cosmos. So what is this information? If the entropy is so vast, what is it actually encoding? The leading idea is that it represents the quantum states of every single particle that ever crossed the event horizon. The specific spin of every electron, the flavor of every quark, the precise configuration of every atom that made up every book, every star, every person that ever fell in. The information isn't destroyed, it is scrambled and imprinted onto the very fabric of the event horizon itself. Think of it not as a cosmic shredder, but as the ultimate hard drive. Its storage capacity is mind-boggling. The surface area of the event horizon is so packed with information that each square Planck area, a size 100 trillion times smaller than a proton, is thought to hold roughly 1 bit of information. This transforms our view of a black hole from a simple gravitational pit into a dynamic, complex object. It is not a cosmic vacuum cleaner, it is a cosmic library. And this is where the profound connection to universe formation emerges. If a black hole is truly a repository of information, and if the theory of a quantum bounce or a white hole eruption is correct, then that information doesn't just sit there. It becomes the most important ingredient in the recipe for a new cosmos. The initial conditions of a new universe, its fundamental constants, its quantum fluctuations, the very seeds from which galaxies would eventually form, could be deeply influenced by the specific information inherited from its parent. The immense entropy of the black hole, a measure of its hidden possibilities, could provide the raw variability needed for the new universe to have its own unique physical laws. It's a process of cosmic transmission. The library doesn't burn down, its entire collection is scanned and used to write the first draft of a new physical reality. The parent universe's history, written in the quantum states of its particles, becomes the genetic code for its offspring. This idea elevates black holes from being mere endpoints to being the most crucial evolutionary link in a possible multiverse. Entities that not only create new worlds but also pass on a legacy of information from one cosmic generation to the next. But to truly grasp the cosmic life cycle, we must consider the most dominant force shaping our universe's long-term fate, a force that might hold the key to its reproductive success: dark energy. This mysterious pressure causing the expansion of the universe to accelerate is not just a background detail. It could be the ultimate determinant of whether a universe is fertile or sterile in the grand scheme of cosmic evolution. The quantity of dark energy, often represented by the cosmological constant in Einstein's equations, might be the single most important factor inherited by a new universe from its black hole parent, setting the stage for its entire future. Think of dark energy as the cosmic climate. In a universe with too much of it, like ours appears to have, the expansion accelerates. Galaxies are pushed apart from one another at an ever-increasing rate. While this might seem destructive, it initially creates a vast, spread-out environment perfect for the formation of massive elliptical galaxies and their central supermassive black holes through galactic collisions and mergers. This early phase could be a boom time for black hole production, but there's a tipping point. If the acceleration continues unchecked over trillions of years, it leads to what cosmologists call the Big Rip or a heat death scenario. Eventually, galaxies become so isolated that they can no longer interact and merge, cutting off the primary fuel supply for growing supermassive black holes. Star formation ceases as gas clouds are pulled apart, and the universe becomes a cold, dilute soup of isolated stars and dead galaxies slowly fading to black. In this ultimate future, the rate of black hole formation plummets to zero. The universe becomes infertile, unable to produce any new offspring. Now, consider a hypothetical sibling universe born from the same parent, but one that inherited a much smaller value for the cosmological constant. In this cosmos, the expansion is far more sedate. There's no violent acceleration to tear galactic structures apart. Galaxies remain gravitationally bound in huge clusters, constantly interacting, merging, and feeding their central black holes. This environment might be a prolific factory for creating new black holes across cosmic time. However, there's a potential downside to this slower pace. A universe with too little dark energy might collapse under its own gravity in a big crunch far too quickly, not allowing enough time for multiple generations of stars to form, forge heavy elements, and create the conditions necessary for robust black hole formation. It needs a Goldilocks amount of dark energy, not too much to cause isolation and not too little to cause a premature collapse, to maximize its long-term reproductive output. This is where Lee Smolin's theory of cosmological natural selection finds a powerful new variable. The random mutations in the physical constants that occur during a black hole bounce could predominantly affect the value of the cosmological constant. Universes that, by chance, inherit a value that fosters an optimal balance between expansion and structure formation would produce the most black holes. They would be the most fit and would therefore have the most offspring. Over countless generations, the multiverse would become dominated by universes with a cosmological constant tuned for black hole production. Intriguingly, our own universe's measured value, while seemingly small, is precisely in the range that allows for both significant galactic structure formation and long-term expansion. It might not be fine-tuned for life, but perfectly tuned for making black holes over a truly cosmic timescale. This perspective places dark energy not as an ominous force of cosmic destruction, but as a crucial regulatory mechanism in a grand evolutionary process. The acceleration of space might be the very thing that, for a time, creates the conditions for prolific reproduction before eventually sealing the universe's fate. The ultimate irony is that the force driving our universe toward a cold, lonely end could be the same force that was selected for over eons of cosmic evolution, because it initially enabled a flourishing of cosmic life in the form of black holes. Our universe's expansion isn't a mistake. It might be a feature, a carefully inherited trait from a long line of successful ancestors, ensuring that for a glorious epoch, it teemed with the potential for new creation. While the idea of black holes birthing entirely new cosmoses is profoundly compelling, it's not the only game in town when it comes to their ultimate purpose. Another school of thought, equally mind-bending, proposes a different destiny for these gravitational giants. Instead of creating something entirely new, could they simply be tunnels, cosmic shortcuts connecting two distant points in our own universe, or even bridges to other, pre-existing realities? This is the captivating realm of wormhole hypotheses, ideas that turn black holes from creators into connectors. The theoretical foundation for this idea is as old as general relativity itself. Just a few months after Einstein published his monumental theory, physicist Carl Schwarzschild found the first exact solution to its complex equations, describing what we now know as a non-rotating black hole. A couple of decades later, Einstein himself, working with Nathan Rosen, took a closer look at the mathematical description of a black hole's interior. They discovered that the equations didn't just describe a one-way plunge to a singularity. They also described a tunnel, a bridge connecting the black hole to another solution, a white hole spewing matter out somewhere else. This structure became known as an Einstein-Rosen bridge, the original mathematical concept for a wormhole. So what exactly is a wormhole? Imagine our universe is the surface of an apple. To get from one side to the other, an ant would have to crawl all the way across the curved surface. But if the ant could burrow directly through the apple's core, it would take a dramatically shorter path. A wormhole is that tunnel through the apple. It's a shortcut through the space-time continuum, a warp in the fabric of reality that could, in theory, connect two points that are impossibly far apart by any normal measure of distance. In this view, the black hole isn't an end, it's one entrance to this tunnel with the white hole serving as the exit. This sounds like the perfect setup for interstellar travel, the kind of plot device that fuels science fiction. There's a crucial catch, however. The original Einstein-Rosen bridge was what physicists call non-traversable. It would form in an instant and then pinch off or collapse faster than any particle or signal could possibly travel through it. It's like a tunnel that forms and then immediately caves in before you can even take a single step inside. For a wormhole to be a practical gateway, it would need to be held open, propped up against the relentless force of gravity that wants to crush it into a singularity. This requires something truly exotic, matter with negative energy density, often called exotic matter. This isn't antimatter that has positive energy. This is something even stranger, a substance that would create a gravitational repulsion, pushing the walls of the wormhole apart to keep them from collapsing. The search for such exotic matter, or a way to generate its effects, is a major frontier in theoretical physics. Some ideas involve manipulating quantum fields in a specific way, perhaps using the bizarre Casimir effect, where the quantum vacuum between two closely spaced plates can exhibit negative energy densities. If such a thing could be stabilized, a traversable wormhole might be possible. This is where the distinction from the universe creation theories becomes so important. In the white hole bounce scenario, the connection to the new universe is almost certainly severed instantly, a one-time birth event. A stable wormhole, however, would suggest a permanent or semi-permanent link, a gateway that could, in principle, be used for two-way travel or communication between two regions of spacetime. This leads directly to the concept of parallel universes. If a wormhole doesn't connect two points in our universe, but instead its exit point lies in a completely separate universe with its own distinct physics and history, then it becomes a bridge to a true parallel reality. This idea is a cornerstone of the multiverse concept that emerges from other theories, like the inflationary landscape. A black hole in our world could be the entrance, and a white hole in another universe could be the exit. It wouldn't be creating that new universe, it would simply be linking to it, revealing a cosmos that already exists independently. Contrasting these two grand ideas reveals a fundamental philosophical split. The universe creation theory, with its black hole bounces and cosmological natural selection, is a story of ancestry and legacy. It's a vertical multiverse, a family tree where each generation gives birth to the next. The wormhole hypothesis, on the other hand, suggests a horizontal multiverse. It's a vast network of pre-existing realities, all floating alongside each other in some higher dimensional bulk space, with black holes acting as occasional, fragile stitches connecting them. One theory is about genesis, the other is about connection. One sees black holes as cosmic parents, the other sees them as potential crossroads. The challenge with the wormhole gateway idea, much like the universe birth theory, is testability. How could we ever know if a black hole leads somewhere else? Some theorists have proposed that if a wormhole's mouth were to pass in front of a distant star, its unique gravitational lensing effect would be subtly different from that of a black hole. Others suggest that the ring-down signal from two merging black holes might contain faint echoes if one of them were actually a wormhole, as gravitational waves could bounce around inside its exotic structure before escaping. For now, these remain tantalizing possibilities, hints we might one day be able to follow to an unimaginable conclusion. Whether they are the architects of new realities or the gatekeepers of distant ones, black holes continue to challenge our understanding of existence itself. This leads us to perhaps the most dizzying implication of all, a thought that inverts our entire perspective on reality. If black holes can be the birthplaces of new universes, then isn't it just as plausible that our own cosmos, with its own ancient Big Bang, began this way? Could everything we see, from the farthest galaxy to the screen you're watching right now, all exist within the event horizon of a black hole that formed in some vast parent universe? It's a hypothesis that transforms our home from a free-floating arena of existence into something more like a cosmic matryoshka doll, a universe nested within another, which itself may be nestled within another in an endless chain of creation. Think back to the moment of our Big Bang. Physics tells us it was a state of incomprehensible density and temperature, a singularity from which space and time themselves erupted. For decades, this has been the ultimate boundary of our knowledge, the uncaused cause. But what if that singularity wasn't a true beginning, but a transformation? What if it was the moment of a quantum bounce at the heart of an immensely large black hole in another cosmos? This idea offers a stunningly elegant solution to the puzzle of the Big Bang's origin. Instead of a universe popping into existence from nothing, it would be the rebirth of matter and energy from a previous state, funneled through the ultimate cosmic crucible. The immense, explosive expansion of our early universe would simply be the white hole eruption, the other end of that tunnel, playing out on the grandest possible stage. This perspective also provides a potential, naturalistic explanation for one of the deepest mysteries in all of science, the apparent fine-tuning of our universe. Why do the fundamental constants of nature, the strength of gravity, the mass of an electron, the cosmological constant, have the precise values that allow for stars, planets, and life to exist? If even one of these numbers were slightly different, the cosmos would be a sterile void. The nested universe idea suggests an answer. The physical laws of a child universe may not be random. They could be inherited with slight mutations from the physics of its parent. A black hole's formation is governed by the laws of its home universe. The properties of the matter that collapses, the nature of its gravity, the very process of the bounce, all of these factors could imprint themselves onto the new cosmos, setting its initial conditions and fundamental parameters. In this view, our universe isn't fine-tuned for us by chance or design. It's simply a universe that inherited stable, life-allowing laws from a parent universe that itself was stable and long-lived enough to produce black holes. It's a form of cosmic natural selection operating across generations. Universes that produce black holes get to have offspring, and those offspring tend to resemble their parents. After countless generations, you'd expect to find universes with physical constants that are remarkably conducive to the formation of black holes, which, as we've seen, are the same conditions that allow for galaxies, stars, and life. We aren't the target of this fine-tuning. We are fortunate bystanders in a cosmos that is exceptionally good at replicating itself. This idea forces a profound shift in our sense of scale and place. Our observable universe is 93 billion light-years across, containing hundreds of billions of galaxies. It is, to our minds, the very definition of vastness. Yet, if this nested universe model is correct, all of this immensity could be contained within the event horizon of a single black hole in a much larger parent reality. That parent universe would operate on a scale so monumental that our entire cosmos would be just one tiny unit within it, and that parent might itself be inside a black hole in a grandparent universe, creating a potentially infinite regress of realities within realities. It's a humbling, awe-inspiring thought that redefines the meaning of big. Philosophically, this turns the concept of a creator on its head. It replaces the need for a singular, external agent with a natural, physical process of procreation. The universe wouldn't need a creator in the traditional sense. It would have a parent. Existence becomes a self-perpetuating cycle, a chain of causality stretching back perhaps forever without a definitive starting point. This doesn't answer the question of why there is something rather than nothing, but it does push that question back into a potentially infinite past, suggesting that existence in some form may simply be a fundamental, eternal property of reality. It's a vision that is both terrifying in its scale and beautiful in its elegant, self-sustaining logic. Now, to truly grasp the breathtaking scale of this cosmic reproduction, we have to venture into one of the most mind-bending predictions of Einstein's relativity, the warping of time itself. We've all heard the classic thought experiment of the astronaut twin who travels at near light speed and returns to find their sibling has aged much more than they have. This is time dilation in action, but near a black hole, this effect is dialed up to an almost incomprehensible extreme. The gravitational pull is so immense that it doesn't just bend the path of light, it stretches and distorts the very fabric of time. Picture an intrepid observer in a super-advanced spacecraft, carefully orbiting just outside the event horizon of a supermassive black hole. From their perspective, time passes normally. They might conduct their experiments, sip their coffee, and watch their clocks tick away the seconds. But if they could look outwards towards the rest of the universe, they would witness a spectacle that defies all intuition. The entire cosmos would appear to be speeding up. Stars would be born, live out their lives, and die in a frantic blur. Galaxies would collide and merge in the blink of an eye. Billions of years of cosmic history would flash by in what feels like mere minutes to our observer. This is because, from the vantage point of that intense gravity, time everywhere else is flowing vastly faster. Now, let's weave this into our narrative of universe creation. Imagine that the moment of the quantum bounce, the explosive white hole eruption that births a new cosmos occurs from the perspective of that parent black hole. It might be a brief, fleeting event, but for the new universe itself, time is a completely different story. The moment of its Big Bang is time zero. From that point on, its own clock starts ticking at its own normal rate. It will go through its entire life cycle, inflating, forming galaxies, nurturing stars and planets, potentially giving rise to life and intelligence, and watching its own black holes form. This entire epic journey, spanning tens of billions of years, could unfold from start to finish in what amounts to a split second from the outside perspective of the parent universe. This creates a truly staggering possibility. A civilization in the parent universe could witness the formation of a black hole and, due to the incredible time dilation, potentially observe the entire lifespan of the child universe it spawns, from its fiery birth to its eventual heat death, all within a human lifetime or even less. The entire majestic history of a cosmos, with all its complexity and drama, would be like a brilliant but fleeting flash from the outside. It turns the act of cosmic creation into the ultimate time-lapse video. This relativistic timescale also adds a fascinating layer to Lee Smolin's theory of cosmological natural selection. The mutation and selection of physical constants wouldn't be a slow, plodding process across eons. For an observer in the parent universe, they could potentially test the fitness of a new universe almost instantly. A new cosmos that inherits poor physical constants might collapse back in on itself or fail to form structures in a fraction of a second from the parent's perspective. A successful, robust universe like our own would showcase its longevity and stability by flourishing for what amounts to billions of years in its own time, even if that is just a brief moment externally. This compression of cosmic epochs into observable instants makes the entire concept of a multiverse evolving through natural selection feel less like a philosophical abstraction and more like a dynamic and potentially observable physical process. The most profound acts of creation might be happening all around us, but they are operating on time scales so alien that we simply haven't learned to perceive them. But what does that journey actually look like for a star, a planet, or, heaven forbid, an entire civilization that takes that one-way trip? Let's follow that path and see where these theories lead the stuff that falls in. From our perspective outside the event horizon, we'd see any object approaching the black hole begin to experience the extreme effects of gravitational time dilation. As it gets closer, its clock appears to tick slower and slower to us. Its light would redshift into deeper and deeper shades of red, then infrared, before finally fading from view entirely as it crosses the threshold. It would seem to freeze in time, a ghostly image eternally stuck on the edge of the waterfall. But for the object itself, if it could survive the immense tidal forces, its experience would be very different. It would cross the event horizon without fanfare, passing a point of no return that offers no visible sign, no flashing neon warning. The journey inward is a one-way slide down the steepening slopes of curved spacetime, drawn inexorably toward the center. According to classical physics, this is where the story ends in sheer terror. The tidal forces, the difference in gravity between your head and your feet, would become overwhelming. This process of spaghettification would stretch and compress any structure into a stream of elementary particles, all racing toward the central singularity to be crushed into a point of infinite density and erased from our universe's history. It's the ultimate cosmic trash compactor, a place where the information about what you were, your atomic structure, your memories, the very essence of your being, is seemingly obliterated forever. But if the new universe theories are correct, this isn't an erasure at all. It's a transformation, a recycling process on the grandest imaginable scale. The matter isn't destroyed, it's repurposed as the raw material for an entirely new cosmic beginning. In Lee Smolin's cosmological natural selection, the information carried by that matter, the specific quantum states of every atom, becomes part of the genetic code for the new universe. Imagine a star that formed heavy elements like carbon and iron in its core through nucleosynthesis. When that star collapses into a black hole, those elements are not lost. Their properties, the very physical constants that govern their creation, could influence the initial conditions of the new Big Bang inside the bounce. The new universe might inherit a slight predisposition for those same constants, a cosmic genetic trait passed from parent to offspring. In this way, the history of a parent universe, written in the elements of its stars and planets, subtly shapes the potential of its children. The holographic principle and the black hole information paradox offer an even more direct method of preservation. If the information of everything that falls in is encoded on the event horizon's surface, then that data isn't lost when the black hole eventually evaporates via Hawking radiation. In the universe creation scenario, that information doesn't even have to wait for evaporation. The quantum bounce or white hole eruption could transfer that entire data, set the library of everything the black hole ever consumed, directly into the fabric of the new cosmos. This leads to a staggering possibility. The quantum information that once constituted a planet, a star, or even the complex chemistry of a living world could be imprinted onto the nascent spacetime of the new universe. It might not arrive as a reconstructed Earth, but as a fundamental part of the background conditions, perhaps influencing the pattern of density fluctuations that later collapse into galaxies. The stuff of ancient civilizations could literally become the foundation for new galactic clusters. This transforms the act of falling into a black hole from the ultimate death into the ultimate act of cosmic legacy. A star doesn't just die, its matter becomes the seed for a new reality. A planet's history isn't erased, its information is archived and rebooted in a new dimension of existence. It suggests a profound interconnectedness between all things across generations of universes. The iron in your blood, the calcium in your bones, were forged in the heart of a long-dead star. If these ideas are correct, those very atoms might one day participate in a far more spectacular event, not just forming a new star, but helping to spark an entire new cosmos, carrying a faint, encoded whisper of a history that spanned galaxies and lifetimes. Of course, the most profound challenge we face isn't a shortage of imagination, but the stark limitations of our technology. How do you test a theory about the birth of an entire universe, an event that by its very nature might be permanently hidden from our view, locked behind an event horizon, or lost in the pre-dawn of our own Big Bang? The truth is, our current tools are like trying to listen for a whisper in a hurricane. We're only just beginning to develop the instruments sensitive enough to hear the faintest cosmic signals. The primary obstacle is one of sheer scale and energy. The physics governing a quantum bounce or a white hole eruption operates at energies 1 trillion times more powerful than anything we can create in our largest particle colliders, like the Large Hadron Collider. We are trying to study the blueprint of a skyscraper by examining a single grain of sand. These phenomena occur at the Planck scale, distances so vanishingly small that they are to an atom what an atom is to our entire solar system. To directly probe this realm, we would need a particle accelerator the size of our galaxy, a clear impossibility with any technology we can even conceive of today. This forces us to become cosmic detectives, searching for indirect clues and subtle fingerprints left behind in the observable universe. The hunt for echoes in gravitational wave data is a perfect example of this ingenious, indirect approach. Right now, our observatories like LIGO and Virgo are incredibly sensitive, but they are also fundamentally limited by quantum noise and the constant, subtle rumbling of the Earth itself. The next generation of detectors is already on the drawing board, and they promise a quantum leap in sensitivity. The Einstein telescope, a proposed underground observatory in Europe, and Cosmic Explorer, a vastly larger L-shaped detector in the United States, would be so quiet and so powerful that they could hear the ripples from black hole mergers across the entire observable universe. With this new data, the statistical search for echoes will move from a tentative maybe to a definitive yes or no. If these repeating patterns in the ring-down signals are real, these observatories will find them, potentially providing our first direct evidence that something beyond a classical singularity exists at the heart of a black hole. Even more exciting is the prospect of the space-based LISA mission, a constellation of 3 spacecraft set to launch in the 2030s. By floating millions of kilometers apart in space, free from terrestrial noise, LISA will be able to detect the low-frequency gravitational waves from the mergers of supermassive black holes, the very events that could be the most prolific universe creators. The signals from these colossal collisions could carry the clearest echoes of all. Beyond listening to space-time itself, we are also building ever better eyes to scan the cosmic microwave background. The Planck satellite gave us an incredible map, but it was fundamentally limited by its resolution and sensitivity. Future missions, like the proposed CMB-S4 project, a massive array of ground-based telescopes in the high deserts of Chile and the South Pole, aim to create a map of the early universe with orders of magnitude more detail. They will be looking for more than just Penrose's concentric circles. They will search for any statistical anomaly, any preferred direction, or any pattern in the polarization of the light that betrays a pre-Big Bang origin. Theoretical research is advancing just as rapidly, providing new clues on where to look. Scientists are now using powerful supercomputers to run sophisticated simulations of these exotic physics. They are modeling what a quantum bounce might actually look like, calculating the precise gravitational wave signature it would produce, and predicting the specific kind of imprint it would leave on the CMB. This isn't just wild speculation, it's a rigorous process of generating testable predictions. The theories are becoming more refined, telling us exactly what kind of needle we should be searching for in the cosmic haystack. Perhaps the most revolutionary developments will come from the realm of quantum computing. The same problems of quantum gravity that stymie our classical computers are exactly the kind of complex, multi-variable problems that quantum machines are built to solve. One day, a sufficiently advanced quantum computer might be able to simulate the conditions at the heart of a black hole or the first moments of the Big Bang itself, not as a rough approximation, but as a true digital analog. It could allow us to run experiments in a virtual environment that we could never hope to create in the physical one, offering us a glimpse into the physics of creation from the safety of a laboratory. The path forward is a combination of patience, ingenuity, and collaboration. It requires the bold vision of theorists to dream up these incredible possibilities, the engineering brilliance of instrument builders to construct the tools to test them, and the painstaking analysis of data scientists to sift through the noise for a signal of something truly new. We may not have the answers today or even in this decade, but for the first time in human history, we are building the machines and the methods that could one day allow us to peer behind the ultimate veil and answer the most profound question we can ask: are we alone in existence, or are we one branch on an infinite, growing cosmic tree? These mind-bending scientific theories don't just challenge our understanding of physics, they force us to confront some of the most profound philosophical questions we can possibly ask about existence itself. If universes truly reproduce through black holes, then we must consider the staggering possibility that we are not merely inhabitants of a static cosmos, but participants in a grand, dynamic process of cosmic evolution. This perspective transforms the universe from a passive backdrop into something that behaves almost biologically, with characteristics we typically associate with living systems: reproduction, inheritance, mutation, and selection. The cosmos may not have DNA, but if Lee Smolin's cosmological natural selection holds, it possesses something remarkably similar: physical constants that are passed down through generations, evolving over incomprehensible timescales to favor universes that are proficient at creating more black holes, more offspring. This isn't just a metaphor, it's a potential physical mechanism that assigns a function, a purpose, to the very existence of stars, galaxies, and the fundamental forces themselves. Their purpose could be procreation on the grandest scale. This line of thinking inevitably leads us to an even more radical question. If the cosmos is evolving, could it also be developing something akin to a cosmic consciousness? The idea isn't as far-fetched as it might seem when we consider the role of conscious observers like ourselves. In quantum mechanics, the act of observation is deeply intertwined with the behavior of particles. Some interpretations suggest that consciousness itself may play a fundamental role in collapsing quantum probabilities into definite realities. If our universe is finely tuned to produce conscious life, and if that life then goes on to observe and interact with the quantum fabric of reality, could we be serving a function within a larger cosmic process? Are we, in a sense, the universe's way of becoming aware of itself? This doesn't necessarily imply a single, unified cosmic mind, but rather a potential for consciousness to emerge as a natural consequence of cosmic evolution, a complex property that arises in universes that are stable, long-lived, and rich in structure. Our own growing self-awareness and our drive to understand the cosmos could be seen as part of this much larger evolutionary trend. This radically alters our perspective on humanity's place in the cosmos. We are no longer insignificant specks adrift in a vast, indifferent void. Instead, we become something far more intriguing. We are the universe's chance to reflect on its own nature and origins. We are the means by which the cosmos can ask questions about itself. Every telescope pointed at the heavens, every particle collider smashing atoms together, every philosopher pondering the meaning of existence, all of it could be seen as the universe consciously exploring its own workings. This bestows upon humanity, and potentially any other conscious life in the universe, a role of immense importance. We are not just passengers, we are the nascent nervous system of a cosmos that is gradually waking up. This is a vision that replaces cosmic loneliness with a deep, intrinsic belonging. Our quest for knowledge is not a petty human endeavor, it is the universe fulfilling its own potential for understanding. With this potential role, however, comes a profound and daunting responsibility. If our universe is indeed a reproductive entity, and if conscious life is a key part of its cosmic ecosystem, then our actions could have consequences that ripple across cosmological timescales. Our responsibility may extend beyond the well-being of our planet and even our own future. It might encompass the very fertility of our cosmos. Could our actions or our failures impact our universe's ability to produce black holes and give birth to new realities? For instance, if a civilization were to advance to a stage where it could harness the energy of stars on a galactic scale, a hypothetical Kardashev-type Roman III civilization, its activities could potentially influence the rate of star formation, galactic mergers, and ultimately the creation of new black holes. The ethical considerations are staggering. Would we have a duty to ensure the reproductive success of our universe? This frames the goal of a long-term, space-faring civilization, not just as a matter of survival, but as a potential moral imperative to act as stewards of cosmic creation itself. Furthermore, these theories challenge our most fundamental notions of life and death. If every black hole is a portal to a new universe, then the death of a star is not an end but a transformation. The destruction inherent in a black hole's formation is revealed as an essential part of a creative cycle. This invites us to reconsider our relationship with entropy, decay, and chaos. They are not merely forces of disorder, but may be the necessary catalysts for new beginnings. On a personal level, this cosmological view can be both humbling and comforting. The atoms that make up our bodies were forged in the hearts of stars that lived and died long ago. If these ideas are correct, those same atoms may one day be part of a stellar collapse that gives rise to an entirely new cosmos. Our physical connection to the universe is not just one of origin, but potentially one of legacy. We are not just stardust, we may be future universe material. This perspective intertwines our fate with the fate of the cosmos in the most intimate way imaginable, suggesting that in the grand cycle of existence, nothing is truly lost, but everything is forever transformed. Of course, we've been exploring some truly cosmic ideas, but it's crucial to separate the revolutionary science from the fantastic fiction that often shapes our imagination. Think about some of the most iconic black hole scenes in movies. In Disney's The Black Hole, the crew flies directly into a swirling vortex, facing fiery landscapes and a literal devil figure inside. It's thrilling cinema, but it's pure fantasy. A real black hole offers no such scenic tour. Crossing the event horizon would be a far more subtle and ultimately destructive affair, with no windows to hell or giant robots waiting on the other side. Then there's the blockbuster Interstellar, which actually consulted with physicist Kip Thorne to get a lot of the science remarkably right. The depiction of Gargantua, the supermassive black hole, is breathtakingly accurate. Its glowing accretion disk of superheated gas and the gravitational lensing warping the background galaxy are based on real physics, but the film takes a creative leap when Cooper falls inside. While the portrayal of the Tesseract, a higher dimensional space allowing him to manipulate time and communicate with his daughter, is a brilliant narrative device, it's speculative fiction. The real interior of a black hole, according to our best theories, isn't a navigable library of bookshelves representing moments in time. It's a one-way street to either a crushing singularity or a quantum bridge we cannot see or interact with. These fictional portrayals often get the what right but invent the what happens next. They accurately show the incredible gravity and the warping of light, but they almost always ignore the lethal tidal forces that would stretch any object into a stream of atoms long before it reached the center. The biggest misconception they promote is that black holes are tunnels we could somehow travel through and survive. In almost every scenario, the journey itself would be fatal. However, these stories tap into a deeper truth we've been discussing, the human intuition that a black hole might not be an end but a passage to somewhere else. The science fiction fantasy of travel is a stand-in for the scientific hypothesis of creation. One is about personal journey, the other is about cosmic genesis. This distinction is vital. When scientists like Roger Penrose or Lee Smolin talk about universes being born from black holes, they are not suggesting we could ever visit these new worlds. The connection, if it exists, is a one-time quantum-scale event that severs the new universe from our own almost instantly. You couldn't send a probe or a message through. The new cosmos expands into its own separate spacetime, forever disconnected from its parent. Science fiction gives us wormholes as stable gateways for starships. Science gives us the possibility of a fleeting, fundamental link in the fabric of reality that operates on a scale and under laws we are only beginning to comprehend. One is about exploration, the other is about explanation. Both are captivating, but only one is built on a foundation of mathematics and testable, albeit challenging, hypotheses. Imagine sitting down for a conversation with Sir Roger Penrose himself, a mind that has reshaped our understanding of reality. When asked about his conformal cyclic cosmology, his voice might carry a quiet, unwavering conviction. He'd describe the mathematical elegance of it all, how the equations themselves suggest that the infinite future of one universe seamlessly becomes the hot, dense beginning of the next. For him, the evidence is written in the sky, in those faint concentric circles in the cosmic microwave background. The Hawking points, he believes, are the gravitational fingerprints of black holes that evaporated in a previous eon. He's not just proposing a theory, he's pointing to what he sees as a fossil record of an eternal cosmos, a story written in the oldest light we can see. His perspective is one of majestic mathematical inevitability, a universe forever renewing itself in an infinite loop. Now shift to a dialogue with Lee Smolin. His energy is different, dynamic, evolutionary, almost biological. He'd passionately argue for his theory of cosmological natural selection, painting a picture of a multiverse that learns and adapts. He'd explain that the laws of physics aren't some divine, fixed edicts. They are the result of trial and error across countless cosmic generations. A universe that successfully makes many black holes has many offspring which inherit its successful traits. He'd likely address the criticisms head-on, acknowledging the challenge of testing a theory about other universes, but he'd counter that it makes a powerful prediction, that the laws in our universe should be fine-tuned for one thing and one thing only, maximizing the production of black holes. For Smolin, our cosmos isn't a static arena, it's a player in a grand, evolutionary game. But what would these two giants say to each other? While both envision a multiverse, their mechanisms are worlds apart. Penrose's cycle is one of majestic mathematical resurrection, where information is preserved through gravitational imprints. Smolin's vision is one of mutation and selection, where information is passed through slightly altered physical constants. In an imagined debate, Penrose might question the mechanism for this mutation, asking how exactly the laws of physics change during a bounce. Smolin might challenge the detectability of Hawking points, arguing that they could too easily be simple noise in the data. Their disagreement isn't a conflict, it's the essential, healthy engine of scientific progress where competing ideas are sharpened against each other. The conversation doesn't end with them. A new generation of physicists is building on these foundations. Researchers like Carlo Rovelli, a founder of loop quantum gravity, would bring a different, granular perspective. He'd steer the discussion toward the quantum nature of spacetime itself, explaining how its discrete, loop-like structure at the smallest scales prevents the formation of a true singularity, replacing it with a bounce. His focus is less on the cosmological implications and more on the fundamental physics that could make such a bounce possible, bridging the chasm between quantum mechanics and gravity. For him, the black hole to white hole transition isn't just a cosmological idea. It's a prediction of a specific mathematical approach to quantum gravity. Then there are the data detectives, like the cosmologists analyzing the Planck satellite data. Their perspective is grounded not in grand theory, but in painstaking observation. They'd express cautious excitement about the search for primordial echoes, whether in the CMB or gravitational waves, but they'd also emphasize the monumental challenge of distinguishing a true signal from astrophysical background noise and subtle instrumental effects. They are the skeptics who keep the theorists honest, demanding rigorous statistical evidence before accepting any claim of a pre-Big Bang universe. Their work is a slow, meticulous grind, but it's the essential process that turns captivating speculation into established science. Hearing these diverse voices together reveals a thrilling truth. This isn't a field with settled answers. It's a living, breathing, and often contentious conversation at the very edge of human knowledge. The disagreements aren't a sign of weakness. They are the signature of a science that is alive and kicking, grappling with the biggest questions we can ask. Whether through Penrose's cosmic cycles, Smolin's evolutionary landscape, or Rovelli's quantum spins, these physicists are all guided by the same fundamental principle: a trust that the universe, in all its mystery, is ultimately understandable and that our human ingenuity, given enough time, will find a way to read its deepest secrets. And so we arrive at the questions that truly bring these cosmic ideas down to earth, the kind of things you'd probably be wondering right about now. Let's tackle a big one head-on. If our universe gave birth to another through a black hole, could we ever send a message to it or even visit? The heartbreakingly short answer, based on everything we understand about physics, is almost certainly no. Think about the mechanism we've been discussing. Whether it's a quantum bounce or a white hole eruption, that new universe doesn't just pop into existence next door. It births its very own space-time, expanding into its own separate dimensions. The connection, the umbilical cord, is theorized to be a fleeting quantum event, a tunnel that pinches off and vanishes almost instantaneously. It would be like trying to send a letter to someone after the only road to their city has not just collapsed but ceased to exist entirely. We are forever separated by the ultimate barrier, the origin event of a new cosmos, but let's indulge in a thought experiment. Imagine we could somehow stabilize that connection, creating a traversable wormhole as we discussed earlier. Even then, the challenges are mind-boggling. First, you have to survive the fall into the black hole, which, let's be clear, involves being stretched into a stream of particles by unimaginable tidal forces, a process called spaghettification. Then you'd have to navigate the chaotic physics of the bounce or the tunnel itself. And even if you somehow did all that, you'd be emerging into the Big Bang of that new universe. You wouldn't be arriving in a place with stars and planets. You'd be arriving into the searing, dense plasma of the universe's first moments, an environment more violent and energetic than anything we can conceive. Communication is just as impossible. Any signal we sent, a radio wave, a laser beam, would share the same fate as matter, lost in the transition or drowned out in the firestorm of a new beginning. This leads to another brilliant question. Would that new universe even have the same laws of physics as our own? Would gravity work the same way? Would atoms and molecules behave as they do here? This is where Lee Smolin's theory of cosmological natural selection gives us a fascinating answer. He proposes that the laws aren't copied perfectly. They are inherited, but with slight, random mutations. Think of it like biological evolution. A child isn't an exact clone of their parent. They have a unique combination of genes. In this cosmic analogy, the fundamental constants, the strength of gravity, the mass of an electron, are the genes. A new universe might have a gravitational constant that's a tiny fraction stronger or weaker. Some of these mutant universes would be stillborn, collapsing instantly or failing to form any structure. Others might be sterile, expanding into cold, empty voids. But the ones that are successful, the ones that can stick around long enough to form galaxies and stars, will be those with laws that allow for the creation of black holes. So while the laws might not be identical, they would likely be similar because those are the laws that proved successful for the parent. Our universe's ability to make black holes might be a family trait. Now for the most personal and terrifying question of all. What would it actually be like to fall into a black hole that's destined to become a new universe? Let's separate the reality from the science fiction. From the perspective of an outside observer watching you fall, your journey would look truly bizarre. As you approach the event horizon, the immense gravity would cause your image to slow down, redden, and eventually fade from view entirely. You would appear to be frozen in time, forever etched on the edge of the black hole. But for you, the brave astronaut inside the spacecraft, the experience would be very different, at least initially. You would cross the event horizon without seeing a magical portal or a flashing sign. It's not a physical surface. But once across that point of no return, the gravitational gradient would become extreme. The pull on your feet would be significantly stronger than the pull on your head, stretching you lengthwise while simultaneously compressing you from the sides. This spaghettification would be utterly lethal. reducing any complex object to a stream of elementary particles long before it reached the central region. But here's where the theory offers a strange kind of solace. If the universe creation idea is correct, then your particles aren't being erased, their information isn't being destroyed. Instead, that information, the unique quantum state of every atom that once made up you and your ship, is being carried inward. In the holographic principle, it's being scrambled and encoded onto the surface of the event horizon. In the quantum bounce scenario, that information becomes part of the raw material for the new universe. Your physical form is gone, but the data that defined it becomes part of the foundation of a new reality. It might influence the very initial conditions of that cosmos, perhaps seeding the quantum fluctuations that eons later will become vast clusters of galaxies. So in the most profound, poetic, and impersonal way possible, your journey wouldn't be an end. It would be a transformation on the grandest scale, a recycling of information from one state of existence into another, contributing to the birth of something entirely new. So let's pull back from the event horizon and see where all this leaves us in the grandest story ever told. We began with a hot, dense Big Bang nearly 14 billion years ago, an explosion of space-time that set everything in motion. For eons, simple hydrogen and helium coalesced under gravity's patient pull, igniting the first stars whose furious nuclear furnaces forged the heavier elements of planets and life. Those same stars, in their death throes, seeded the cosmos with these elements and collapsed into the first black holes, the gravitational engines around which galaxies would eventually swirl. Our universe evolved from a featureless fireball into a complex tapestry of light, dark matter, and these mysterious dark anchors. This narrative of cosmic evolution has always followed a certain logic, from simplicity to complexity, from energy to matter, from chaos to structure. But the idea of black holes as universe creators injects a stunning new chapter into this story, one that transforms evolution from a linear process within a single cosmos into a cyclical, perhaps even recursive, process across a multiverse. It suggests that the ultimate purpose of all this stellar activity, the birth of stars, the formation of galaxies, the slow dance of cosmic structures, might not be just to create a hospitable arena for life, but to produce the very engines of cosmic reproduction, black holes. In this view, a galaxy isn't just a collection of stars, it's a nursery for new realities. A supermassive black hole isn't just a monster at the center, it's a potential parent. This reframes the entire timeline of existence, from the quantum to the cosmological. The quantum fluctuations in the early universe, which seeded all future structure, might themselves have been inherited from a prior cosmic cycle. The formation of every star that ever lived could be seen as a step in a grand cosmic life cycle, all leading toward the profound transformation of collapse and rebirth. Even the mysterious dark energy, accelerating the expansion of our universe and seemingly driving it toward a cold, lonely end, might play a crucial role. This acceleration allows for the vast separation of galaxies necessary to form giant elliptical galaxies and their central black holes through mergers, while ultimately ensuring that the newborn universe will be forever isolated and protected, free to evolve on its own. The ultimate fate of our universe, often seen as a bleak heat death, takes on a new, hopeful meaning in this light. The long, dark era that lies trillions of years in the future, when the last stars have died and the black holes themselves slowly evaporate via Hawking radiation, is not an end. It is the final act of preparation. As Roger Penrose envisions, this empty, timeless state becomes mathematically identical to the hot, dense beginning of a new Big Bang. The death of our universe becomes the conception of the next. The information encoded in the evaporation of every black hole, the story of everything that ever was, might be imprinted onto the fabric of the new cosmos, becoming the seeds for its own future galaxies. The cycle begins anew, This is the most profound vision of cosmic evolution possible, a universe that has not only evolved but has learned how to replicate itself. The laws of physics themselves may not be arbitrary fundamental truths, but the evolutionary product of countless cycles of selection, fine-tuned over eons to maximize the potential for creation. We find ourselves in a universe that seems perfectly tailored for life, not because of a divine creator, but because we are the offspring of a long line of successful, fertile universes. Our existence, our ability to ponder these very questions, is a beautiful and intricate byproduct of a cosmos that has mastered the art of being reborn. We are not just living in a universe, we are living inside a cosmic legacy. So where does this incredible journey leave us? We've ventured from the terrifying singularity to the hopeful quantum bounce, from Penrose's cyclical eons to Smolin's cosmic evolution, and from the preservation of information to the mind-bending possibility that our entire reality might be nestled within a black hole of a grander cosmos. The evidence, while still speculative, is compelling not because we have direct proof, but because it emerges from a desperate need to solve the deepest puzzles in physics. The black hole information paradox, the fine-tuning of our universe, the nature of the Big Bang singularity, these aren't just isolated problems. They are screaming clues that our current understanding is incomplete, and the idea that black holes are universe creators offers a breathtakingly elegant framework that ties them all together. It transforms the most destructive objects in the cosmos into the ultimate engines of creation, suggesting a cosmos that is not static, but alive with a dynamic cycle of death and rebirth. Yet, we must stand in awe of the sheer audacity of these ideas while also acknowledging their current limits. This is the cutting edge, the frontier where mathematics and imagination meet. We do not yet have that single, smoking gun observation, the undeniable echo in a gravitational wave signal, the unequivocal pattern in the cosmic microwave background, that would shift this from a beautiful hypothesis to established theory. That crucial step requires patience and even more advanced technology, but the very act of searching is a testament to our species' unyielding curiosity. We are cosmic detectives, piecing together the clues left in the faint afterglow of creation and the ripples in space-time, refusing to accept that any horizon is truly final. This quest is about far more than just understanding black holes. It's about our place in the grand scheme of existence. It asks us to consider that we are not just living in a universe, but within a legacy, a potential offspring of an immense cosmic family tree. It suggests that the iron in our blood and the calcium in our bones, forged in long-dead stars, might one day participate in the birth of a new reality. This perspective is both humbling and empowering, connecting us to the cosmos in the most intimate way imaginable. We are not passive observers, we are the means by which the universe begins to understand itself. Our questions, our theories, and our relentless pursuit of knowledge are the cosmos waking up to its own nature. What do you think? Does the idea of a cosmic life cycle where universes are born from black holes resonate with you? Does it feel like a satisfying answer to the mystery of our own Big Bang? Or does it open up even more profound questions about what came before? I am endlessly fascinated by these conversations, so please share your thoughts and your own mind-expanding theories down in the comments below. Let's keep exploring the unknown together.